Oh, and today we're going to do 7.3, the ambiguous case, which is all about when you're given side-side angle. Remember that in 7.1 we have law of sines that we can always use when we have angle, angle, side, or angle, side, angle pretty efficiently because you're given something like angle, angle, side, or angle, side, angle. If I'm given angle, side, angle, we all know that triangles are always add up to 180, so therefore I can find C pretty naturally. And then I have this sort of pair where I can do that law of sines relationship. Versus angle, angle, side, I have that pair right away. And then when we did 7.2, which is law of cosines, you would do that when you're given side, angle, side, something like this. Let's see, B, A, C. Because here I don't have any given pair, but remember law of cosines helps me create this pair because law of cosines is, a squared equals b squared plus c squared minus 2bc cosine of a. By plugging all this stuff in, the stuff that I was given, I can find a and therefore get my pair and then do law of cosines. However, when we do side-side angle, your first instinct, if you look at a side-side angle triangle, is that. But when I'm looking at a triangle with side-side angle similarity, it would look like this. Well, I would have side, so A, I'd have a side, so B, and then I'd have an angle A. You might be tempted to say, well, I do have a pair and I can use law of sines. The problem is, if you recall back to geometry, side-side angle is not a congruence thing. There's a whole bunch of weird situations that we have to talk about. So whenever side-side angle comes up, we have what's called a potential ambiguity. So for example, here I have angle side side or side side angle. I also here have side side angle. Technically, this triangle can exist as well as this triangle, even with those exact same measurements, because I don't know those other pieces. I don't know big A, little a, or big B. So it creates this weird interaction of technically, is that 17 right here? Which would be here in this vision, or is it right here, so out here? So I don't really technically know. So side C could be a pivot, that'd be right here, this 17, this sort of thing, where A is this hinge of, do I have that angle, or do I have that angle? So we have to look into some specific situations. Those specific situations are as follows. One, if theta is obtuse, the angle you are given, and my opposite is smaller than my adjacent, no triangle exists, which should make sense. In a triangle, the three angles add up to 180. So if angle theta is obtuse, it's over 90, which means it has to be the biggest angle, and therefore the opposite should be the biggest side. So if it's not the biggest side, therefore that triangle doesn't even exist. It would fail the inability to be a triangle. Now, if theta is obtuse and opposite is bigger than adjacent, one triangle exists. Again, that makes sense because my opposite side is opposite of the theta, which is obtuse. Therefore, my opposite would be the biggest side of the triangle, just like, obviously a hypotenuse in a right triangle. Now, there are the other cases. If theta is acute for all four of the next ones, we have to create a height because we get some weird situations. So I would draw a height from this angle right here, where this height is now perpendicular. Now, I need to find my h for all of these. So if I'm going from theta, I could say that my adjacent is now my hypotenuse. And H is kind of like my opposite of just this triangle. And therefore, I could do sine of theta equals opposite H over my hypotenuse, my adjacent. And I can multiply both sides by my adjacent length. That's why we get this formula right here, H equals adjacent times my sine of theta. So, if H is bigger than my opposite, that triangle doesn't exist either, which should make sense if I just think about this triangle right here. So if I redraw that triangle, but I know that H is bigger than my opposite. This triangle can't exist because in the context of this triangle, my opposite would be, a hypotenuse of this smaller triangle. Because if this is 90 for my height, this also has to be 90. That's why I drew this 90 right there. And therefore, that triangle can't exist, and my overarching triangle can't exist either. If theta is acute, and I find my h, and it is smaller than my opposite and smaller than my adjacent in this inequality order, we get two triangles that could exist. This one and this one, where theta is right here. If I can move that. Theta should be right there. Okay. Another situation is where my height is exactly my opposite. That has to be a right triangle because remember the height forms a right angle. And if this number is exactly the same as that number, then therefore my opposite is actually forming that and my adjacent becomes the hypotenuse. And then last but not least, my opposite, if that's bigger than my adjacent, therefore this has to be one triangle that exists. So let's look at some examples. So here, if I look at this, this is obviously my theta. 54 is going to be my opposite, and 62 is going to be my adjacent. So I can already tell that 40 is obviously an acute. So I don't have to worry about either my first two situations. Now, my opposite is smaller than my adjacent, but I need to figure, so I can't be this one. But all these other ones involve the height. So I need to calculate my height. So height would be, adjacent times sine of theta. Therefore, h is going to be 62 times sine 40, or 39.9. Following that logic, my height is less than my opposite, which is also less than my adjacent. So situation 4 would have to be true. There are two triangles that exist here, which means I would have to create and find both triangles, where it could look like this one, or it could look like this one. That change, remember, is this 54. Is the 54 right there, or is the 54 right here, or to level out there? So I have to find that 54, which means, well, let's try it. Those two different triangles are sort of connected, and we use angle B as sort of the connecting piece. So earlier, B was sort of our pivot angle or our hinge. Or, I'm sorry, in this context, angle C would be the hinge. I define hinge as the angle that's between the two given sides. So here, you see how C could be this small angle right here. I should use a different color. Could be this angle right here, or it could be this angle right here where that 54 swings. So B is the third angle. It could be either situation. So it all depends on how this 54 lays, and therefore it affects my height. So if 54 would be right here, my B would be right here, which is perfectly fine. Or if 54 would be right here, my B would be this angle right here, blue. Interestingly enough, if I look at just this triangle right here, this is 54 and this is 54. So therefore, these are isosceles. This is an isosceles triangle, which means this angle right there has to be congruent to that angle with the double blue arcs. Therefore, if I'm looking at it logically, this blue angle and this red angle form a line. Therefore, B and the other B have to equal 180 degrees from that isosceles triangle relationship. For the sake of simplicity, or trying to be conciseness, we are going to use an apostrophe. Remember, from geometry, that just means prime. So just to help denote the different triangles there. So let's actually solve this. For example, we should technically, again, find the height, even though we know what the height is, or that height would be my adjacent times my sine of theta. So my adjacent being 62, my sine being 40, 62 sine 40, 62 sine 40, make sure we're in degree mode. We get, that 39.9. So again, we're getting option 4. My h is less than my opposite, which is less than my adjacent. So let's find them. Now that I know the triangles exist, we still technically do have this pair, so I can use law of sines. So we would get, let's see, sine of 40 over 54 equals sine of b over 62. Multiply both sides by 62. And then I could get 62 sine 40 over 54 equals sine of b. And then, of course, we can inverse sine both sides. So I get sine inverse of 62 sine 40 all over 54, which I can type right into my calculator. And we get 47.8 or 47.5. So let's just say, yeah, 47.6. Then another way you can think about it is, technically speaking, this 62 sine 40, remember, is the same thing as our h. So if you felt more comfortable doing that, you should get the same thing either way of 47.6 degrees. By that logic, we can then find angle C, because C is going to equal 180 minus 47.6 minus 40. So C has to be 92.4 degrees. And then last but not least, we can find little c through law of sine. So C equals sine 92.4 equals 54 over sine 40 times both sides by sine 92.4. So little c equals 54 sine 92.4 over sine of 40. So little c, we'd get 83.9. Okay. Now, technically speaking, as we said earlier, there are two triangles that exist. That would be triangle 1. I would need to find the second triangle. So if I were to find the second triangle, I would start with the idea that angle B and B prime, B plus B prime are supplementary. So to find B prime, I would do 180 minus 47.6. And I get 132.4. And then from there, everything else is the same. I'd find my new C's. So C equals 180 minus 40 minus 132.4, 132. C would be 7.6. And then little c would be the same process. I'm sorry, I should put primes on this. And then little c prime over sine 7.6 equals 54 over sine 40, because a doesn't change at all. So a was given, so I would keep that information. So c, little c prime, would equal 54 sine of 7.6 all over sine of 40. So little c would be then 11.1. Okay. A plane is flying north with an airspeed of 170 miles per hour, the heading of 52 degrees. Its true course is 64 degrees from due north. Wind currents are 40 miles per hour. What are the possibilities for ground speed? So, quick refresher on navigation. We start from true north, so that's where I get 52 right here, and 64 right here. If I were to draw just the triangle I have, though, naturally the angle is actually going to be subtracting those. So it's going to be 8 degrees right there, or 12 degrees. Math. Now, I have to check because I am given this 170 and this 40, so I have side angle. So I need to check the cases, aka I need to find my H. Because opposite is smaller than my adjacent, I then need to find my H. So remember that H would be from B, it's either going to be right here or right here. So I would need to do H equals opposite 40 times sine of 12. 40 sine 12. We get H is 8.3. I'm sorry, 170 sine 12. 170 sine 12. H is 35. Oh, goodness gracious. 70 sine 12. H equals 35.3. Again, we get the situation where H is less than my opposite, which is also less than my adjacent. This is situation number 4 again, the same one where we just had, where there are two triangles. This one specifically asks for the possibilities for ground speed, which would be side length C. So it's going to factor that stuff in. So I need to find both situations of C, whether it stops right here or whether it stops right there. So let's find what we can. Obviously, we can find B right away in triangle 1. So I would get sine of 12 over 40 equals sine of B over 170. Multiply both sides by 170. Inverse sine, so I can do sine to the inverse of 170 sine of 12 all over 40. Again, remember that that top part is the same thing as h. So if you want to think about it as sine to the inverse of h over 40, which should make sense there from that second triangle that's created. So we can do second sine of h divided by 40. And we're going to get, about 62.1 degrees. So B is going to be 62.1 degrees. And therefore, I can find C. C equals 180 minus 12 minus 62.1. C is going to be 105.9 degrees. So I get little c over sine of 105.9 equals 40 over sine 12. Multiply both sides by sine of 105.9, so little c equals 40. Sine 105.9 all over sine of 12. And we get c is going to be 185 miles per hour. But remember that technically it creates two triangles, so I have to go through the second triangle. So remember that it would start with B prime equals 180 minus 62.1. Come on, come on. 180 minus 62.1, 117.9. And then I could find C, therefore C prime equals 180 minus 12 minus 117.9. So C prime is now going to be 58.1. Therefore, little c prime over sine of 50.1 has to equal 40 over sine 12. Multiply both sides by sine of 50.1, so little c prime would equal 40 sine of 50.1 all over sine 12. And we get that little c could also have been 147.6. So in general, that's kind of how the ambiguous case works. The biggest thing it would be to note these 6 changes here, or an easier version right here. When obtuse, kind of more straightforward. When acute, you have to keep track of all 4 of these different situations. Thank you for watching, and I hope you have a wonderful